In this lecture, what we're going to be doing is taking a look at a slightly different form of the first law for open systems, and that is a form that involves unsteady flow. The version of the first law that we will look at is one that could be applied to either charging or discharging of pressure vessels. So we'll begin the lecture with that, and then we will work a couple of example problems dealing with the first law that recap some of the things that have been presented in the last couple of lectures. So we're dealing with processes that involve changes to the control volume with time. So they are no longer steady flow, they're unsteady flow. And I mentioned examples. So charging a vessel, a rigid vessel from a supply line, for example, you might have a pressure vessel connected to a compressed air line. You open a valve and that pressure vessel will then charge. Another one is discharging a pressurized vessel. And if you look to the right now, you'll see a short video clip showing discharging of a pressure vessel and what happens through the process. So let's watch that. So you'll notice a couple of things from the video. First of all, it was very loud when you're discharging a pressure vessel. The other thing you probably noticed was that there was some liquid coming out of the bottom of the tank as we were discharging it, and even ice was forming. What happens is that we have water vapor through the compression process that comes from the atmospheric air, and when we quickly discharge a vessel, it gets very cold. And as a result, the water vapor that would be in the air condenses, and it will even freeze sometimes. So that was what was going on in that video. There are ways that we can handle or study these types of processes and analyze them using the first law. And one of the things that we will do is we make a couple of approximations under what is called the uniform flow process. So what the uniform flow process assumes is that the state of the entire control volume is uniform throughout. That means that you do not have gradients, be it pressure or temperature, within the control volume. You're assuming that the state is uniform throughout. Another thing that you assume is that the fluid flow at the inlet or the exit is uniform and steady. If properties are changing during the process, what you are supposed to do under the uniform flow process is average between the initial and the final states for either that inlet or that exit. So let's take a look at the form of the first law for a uniform flow process. So on the left we have heat transfer. Next is work. Then we have the mass that is exiting, and it is multiplied by the enthalpy of the exiting fluid. Next we have is mass in times the enthalpy. And finally, the last term here is the change in internal energy of your control volume. So that's a form of the first law that we can use for cases where we have unsteady flow under the uniform flow approximation, or assuming it to be a uniform flow process. Now, another thing that I should point out is you'll notice we're missing a couple of terms. We're missing both the kinetic energy change as well as the potential energy change. So the above equation neglects both of those. So that is the equation for a uniform flow process. What we'll do now is we will work a couple of example problems that help demonstrate some of the ideas that we've been looking at with regards to the first law.